In this module, we use the kinetic theory of gases to derive the pressure of an ideal gas from the motion of individual particles. Using the simple assumptions introduced in the kinetic theory of gases, we can now describe gas pressure in terms of the motion of individual particles. The idea that gas pressure results from collisions of particles with the walls of a container is a central concept of the kinetic theory of gases. By analyzing a single molecular collision using classical mechanics and then extending the result to a larger number of particles, we arrive at one of the most fundamental results in the physics of gases. This derivation represents one of the key achievements of the kinetic theory of gases. It also serves as an important test for the applicability of the assumptions we made about the behavior of an ideal gas. The presented line of reasoning goes back to the work of Daniel Bernoulli. He proposed as early as the year 1738 that gas pressure arises from the impacts of moving particles. Later, in the mid-19th century, Rudolf Clausius, James Clerk Maxwell, and Ludwig Boltzmann developed this idea into a full theory. They introduced statistical methods and connected microscopic motion to macroscopic observables. The derivation we now follow builds on their foundational work. Let us now imagine a gas enclosed in a container with a chosen Cartesian coordinate system x, y, and z. We consider collisions of gas particles with one specific wall, a wall perpendicular to the x-axis. We focus first on a single gas particle of mass m moving with the velocity v. This velocity has three components: vx, vy, and vz along the x, y, and z axis. We are primarily interested in the component Vx because it determines how the particle moves towards and away from the selected wall that is perpendicular to the x-axis. We also introduce the momentum of a single gas particle. To avoid confusion with pressure, we denote it by bold P. It is defined as the product of the particle's mass and velocity. Now imagine that this particle approaches the selected wall and undergoes a perfectly elastic collision. This means that the total kinetic energy is conserved as the particle simply bounces off the wall. Before the collision, the x component of the particle's momentum is mvx. After the collision, the particle moves away from the selected wall with velocity minus vx. So the x component of its momentum becomes minus mvx. The change in the particle's momentum resulting from this elastic collision is therefore minus 2mvx. According to the principle of the conservation of momentum, the change in momentum of the wall is the negative of this value, 2mvx. At the same time, the components of the particle's momentum along the other axis do not change. The cumulative effect of momentum transfer from a very large number of individual particle collisions with the walls of the container is the key microscopic mechanism of the macroscopic pressure of a gas. Our next goal is to calculate the total momentum transferred to the wall during a time interval delta t. To do this, we must determine how many particles collide with the wall in this time. This figure illustrates the idea that we employ to calculate this value. It shows that only particles within a distance Vx times delta t from the wall and moving towards it can reach the wall during the given time. Now we consider collisions of gas particles with a part of the wall with an area A. The volume from which particles can arrive is then given by A times Vx times delta t. Due to their random motions, the particles are distributed uniformly. To quantify this distribution, we introduce the particle density n tilde, an intensive quantity defined as the number of particles N per volume V. According to this definition, it is equal to molar concentration multiplied by the Avogadro number. Therefore, the number of particles in this volume is given by n tilde times A times Vx times delta t. Since we assume that the particles are moving completely randomly, we conclude that at any instant, half of the particles are moving towards the wall and the other half are moving away from it. This introduces a factor of 1/2 in the number of particles that are able to collide with the wall during a given time interval delta t. These are the particles that are not only sufficiently close to the wall, but also are moving in the right direction. Therefore, this expression is the average number of collisions with the wall in time delta t. The total momentum transferred to the wall in time delta t is the product of the number of collisions with the wall during time delta t and the momentum change per wall particle collision. The result of the multiplication is n tilde times a times m times vx squared times delta t. According to Newton's second law of motion, the force is the rate of change of momentum. Therefore, the force exerted on the wall is equal to the total momentum transferred to the wall during the time interval delta t divided by the same time interval delta t. The time interval cancels out, leaving an expression for the total force equal to n tilde times a times m times vx squared. The pressure is defined as the force divided by the area on which the impact occurs. We divide the total force by the area and the area cancels out. This gives P equals n tilde times m times Vx squared. Not all particles move with the same velocity. To correctly calculate the pressure, we need to average the previously obtained expression over the motion of all particles. Only the velocity component in the x direction varies between particles, so only it needs to be averaged. But here's the issue. If we simply average the velocities in a given direction, such as the direction of x. For all randomly moving particles, we obtain the result of 0. Here, angle brackets indicate the average or mean value of an expression inside. That is because, as we have pointed out before, for every particle moving in the positive x direction, there is on average another particle moving in the negative x direction. Therefore, their motions cancel out and the mean value of Vx is 0. However, the pressure depends not just on the velocity of particles, but on the square of the velocity. This is an important distinction. Instead of averaging Vx, we have to average Vx squared, which is always positive. This gives us a meaningful non-zero measure of how strongly the particles contribute to the pressure in the x direction. The pressure is now given by n tilde times m times Vx squared in angle brackets. Here, this expression indicates that we take the square of the velocity component along the x-axis for all particles and calculate the mean value of this parameter. I would like to stress an important distinction between the mean square of particle velocities and the square of the mean particle velocities, which is 0. Now, because the motion of particles is random, it is also isotropic, meaning that there is no preferred direction. Thus, the mean value of Vx squared, Vy squared, and Vz squared are all equal. Furthermore, according to the properties of the Cartesian coordinate system, square of the magnitude of the total velocity v is the sum of the squares of its components vx, vy, and vz. Averaging both sides in this expression over all particles gives mean of square of the total velocity v equals the sum of mean squares of vx, vy, and vz. Considering that mean squares of all velocity components are equal, the mean square of the total velocity v is 3 times the mean square of the particle's velocity projection onto any axis, such as x. The important conclusion that we draw from here is that the mean square of the particle's velocity projection onto any axis, such as x, is 1/3 of the mean square of the particle's total velocity v. The mean value of the square of particle's total velocity is a physically meaningful and useful quantity. We define a new quantity characterizing it, the root mean square velocity VRMS, which is the square root of the mean of the squares of the particle's velocities. The mean square of the particle's velocity projection onto any axis, such as x, can therefore be represented as 1/3 of VRMS squared. Substituting this into the earlier expression for pressure gives P equals 1/3 of n tilde times m times the square of the particle's root mean square velocity. Notably, although we originally considered a selected direction x, the final expression for the pressure does not contain direction-specific terms, as expected. This equation is one of the key results of the kinetic theory of gases. It directly connects a macroscopic quantity pressure to microscopic properties of the gas particles, namely their mass, particle density, and root mean square velocity.